I'll be talking about Pelagia noctiluca in the Mediterranean Sea. And if your ears hurt when I say Pelagia, I got really confused about the pronunciation a few days ago. So I went to the fountain of wisdom called Google and checked how it's properly pronounced. And actually, Pelagia would be how the ancient Romans would pronounce it. So this is classic Latin pronunciation. While the modern Latin, called Church Latin, would pronounce it as Italians do, which means like Pelagia. But I will stick with my Slavic and ancient Latin pronunciation. So I'll be talking about Pelagia. My co-authors are Davor Lucic and Alenka Malej, who is sitting there in the audience. And let me start. I know that most of you know Pelagia very well, but anyway, for the others, it has a very painful sting. And I almost hear the Australians laughing now because with their comb jellies, but for us Europeans, this is very venomous. It has no polyp face, so it's completely pelagic, and it performs these pronounced vertical migrations. It dives several 100-meter deep over during the day, and then rises towards the surface during the night. Now, our story begins in the northern Adriatic Sea. This is the square you can see there in the map. This is also where our station is located. And this area is actually subject to very sporadic Pelagia blooms. You can see that on the timeline on the top of the image, where we had like a decade of very frequent blooms beginning at the end of the 70s. But then we had almost a 20-year gap afterwards, and then again some sporadic occurrences after 2004. Now, of course, we're interested what is the main mechanism causing this, and me coming from physical oceanography, of course, the first thing I would think about is currents. For that purpose, we use the product from the Copernicus Marine Service called Mediterranean Sea Physics Reanalysis, which gives us currents from 1987 onwards. Sadly, you can see that 1987 is the exact year when the major bloom ended. So sadly, we cannot model that period. We can focus only on the later years. We coupled these currents with an open drift, open source particle tracking tool. This is a program code which seeds fictional particles into an area and then advects them according to the currents from the other model. So we wrote a special module for open drift, which seeded 10,000 particles in the northern Adriatic on the years when Pelagia was observed. And then we ran the simulation backwards in time for 2.5 years. And the particles performed vertical migrations, as described before, so diving deep during the day and then rising towards the surface during the night. The minimum depth was 500 meters, or at least 5 meters above the ocean floor. And there is a result of such a simulation which shows these tracks in time. The next one. So these are the results. This is the density of particles for all the simulations summed together. And of course, you can see them going down through the Adriatic Sea, but then you can see two paths after that. It diverges. One goes to the Western Mediterranean Sea, which is, of course, a very plausible source of Pelagia. There are very frequent sightings there. Maybe you saw, I hope you saw the poster yesterday. Sonia was presenting with sightings of Pelagia, which shows very frequent sightings in Balearics and that area. So this is a good kind of result. But on the other hand, there is also another path coming from the Aegean Sea, which is marked with the letter A. And actually, we don't know much about Pelagia in Aegean Sea. Maybe some of you do. We don't. This opens three possibilities. One is that there is a more or less permanent Pelagia population in the Aegean, and it seeds the jellyfish towards the Adriatic. Or the other one is that the Aegean is just a stepping stone, so maybe the jellyfish are coming to the Aegean from another area, maybe Western Mediterranean, and then up to the Adriatic Sea. And the third one is that this path actually exists, but there is no jellyfish in the Aegean Sea, so they don't come from that area, actually. But then we decided to make things a little bit more complicated. and we seeded the particles from the Western Mediterranean Sea. And we seeded 3,600 particles, ran the simulation for 2 years. You can see them dispersing through the Mediterranean Sea. And then we took a step further and decided to introduce food-dependent mortality and reproduction and growth to make it a proper individual-based model. Again, we turned to Copernicus Marine Service and used the biogeochemistry analysis, which is available from 1999 onwards. Now, what we did was, let me rephrase that. So we decided that each of the particles will represent a certain number of individuals, or maybe a certain biomass. Actually, at this point, this model is very abstract, and there is no difference between that. So it represents a certain number, let's say 10,000 individuals, and this number changes according to food availability. Now, how to do that? We use that equation, which is written up there. I know some people are afraid of equations. Please don't be. This one is quite straightforward, so I'll go. If you can see the curve there, this is the tangents hyperbolicals that was used in our calculations. It is a function that saturates at a certain value. That's why we chose this function. Our basic idea is that actually after a certain threshold, the food availability doesn't limit the growth anymore. And then, so the PP in the equation is primary production. dn's n is actually the change of number of particles in time. Individuals. And the k are 4 parameters of this equation, which determine its stretching in vertical and horizontal direction, and its translation left, right, up, and down. So we ran 2.2 million simulations with this equation. Why? Because we have no idea about the value of these parameters. So at each simulation, we just changed the parameters slightly and reran our 2-year run. And after the run, we decided that we want to keep the initial population quite stable, which means that the particles that have left the initial area had to be replaced with growth of number of individuals of the particles that stayed in the area. And in the end, the difference should be less than 20%. So we kept only the simulations that did this. So from 2.2 million simulations, we were left with 13,000 simulations, but they're placed in this 4-dimensional space. We have 4 parameters, which are changed, and we are looking for aggregations in this 4-dimensional space, which would indicate that we are onto something, that these parameters actually have some meaning. So sadly, humans are not made to think in 4 dimensions, but luckily we have artificial intelligence, so we use the k-means clustering to search for clusters in this 4-dimensional space and return the centroid values, which would be the values of k, and use this to perform multi-year runs. Now, I'm good with time. Okay, but even so, there are 3 plots on the right side that show the shape of our curve depending on these parameters. So these are some of the clusters that were chosen by the machine, by the algorithm. And the top one, as you can see, saturates very quickly, so actually dependence on food concentration is very low. And actually, it's always positive, so there is no mortality. And so discarded configurations like that. This is completely unrealistic. The bottom one is almost linear, so there is no saturation. And we want saturation, so we discarded the configurations like that as well, and kept only those that were similar to the middle one, where you have mortality below certain primary production value, and where you have saturation above certain threshold. But sadly, even among these, most are unstable. So the population goes extinct in 4 years or explodes, and all of a sudden we have millions and millions of particles running around, which is computationally unfeasible. But here we go. Some of them actually look quite well. This is one of these. This is the 6th year of simulation. The scale, the color scale is logarithmic. And you can see that kind of a very strong population established itself between the Balearics and, for example, Sardinia. And this is something that we would expect to happen. And then there is export of particles towards the Eastern Mediterranean, but their numbers are starting to drop quite rapidly. They're turning blue and green. And you can also see some particles entering the Adriatic Sea, which makes us living there very happy. So this is more or less preliminary work. It's actually started as a side project, but I kind of got in love with it. It's really nice to see patterns, developing from very basic principles, but in the end, mimicking something that is really close to what you see in nature. So, as said, we have a very small number of very basic assumptions to form our model. There are many other things that maybe should be taken into account or not. We'll see. We'll try some of those. For example, we have loggerhead turtle abundance on the right, a paper that was published last year, and I just actually found out about it a few days ago. And that, for example, would enable us to introduce spatially variable mortality. So this is work in progress. There are things to be done. But yeah, I must admit I'm quite happy with the results. So I acknowledge the funding from our agency, and I thank Tinkara as always for her support in this work. Thank you.